So urban setting has some interesting challenges. We studied those in UTM project where we learned that GPS is not always reliable, communication link is not always reliable in certain corners of urban airspace. So we want to make sure that the aircraft in this case is able to fly those missions that they will typically experience in urban airspace.
You're listening to the Drone Radio Show podcast, the show about drones and the people who use them for business, fun, and research. Hosted by Randy Goers.
Hello, everyone. This is Randy Goers, and welcome to the Drone Radio Show podcast, episode 257. What's NASA doing in the area of unmanned aerial systems? For that question, we head to the NASA Ames Research Center in Mountain View, California, to speak with Parimal Kopardekar and Misty Davies. The Ames Research Center is one of 10 NASA field centers. Since 1939, Ames has led NASA in conducting world-class research and development in aeronautics, exploration technology, and science aligned with the center's core capabilities. The Ames Research Center supports virtually every major NASA mission and initiative through its expertise in aerosciences, air traffic management, advanced computer and IT systems, and many other capabilities. Dr. Parimal Kopardekar, or PK for short, serves as a director of NASA Aeronautics Research Institute. In this capacity, he is responsible for exploring new trends and needs related to aviation in the areas of autonomy, aeronautics manufacturing, and advanced air mobility. Dr. Misty Davies is a computer research engineer at NASA Ames, working within the robust software engineering technical area. Her work is focused on predicting the behavior of complex engineered systems early in design as a way to improve these systems' safety, reliability, performance, and cost. In this edition of the Drone Radio Show, PK and Misty give us an update on the work NASA is doing to support unmanned aerial systems. They talk about the challenges of developing autonomous systems, and they provide some insights into NASA's grand challenge for urban air mobility. But before we hear from PK and Misty, I want to thank those of you who are supporting my funding campaign. Whether it's $1, $100, or much more, you can help defray the cost of production and keep the podcast going and growing. Go to droneradioshow.com/donate. So let's get an update on what NASA is doing in the area of unmanned aerial systems. Let's pick up the interview where I asked PK and Misty to introduce themselves.
My name's Dr. Misty Davies. I'm the Deputy Project Manager for a NASA project called System-Wide Safety.
And I'm Parimal Kopardekar. I go by PK. I am Director of NASA Aeronautics Research Institute and also Senior Technologist for Air Transportation System.
PK, can you give us an update on what NASA is doing in the area of unmanned systems?
We have a number of initiatives going on at NASA. First is focused on unmanned aircraft system traffic management, which is really enabling the low-altitude, small drone operations. We are postulating that there will be millions of these operations in a few years, and accommodating them in a safe and efficient manner is something that we are focused on. So that's one area. Second initiative we have is larger drones, enabling these larger unmanned aircraft systems in all types of airspace is another area that we are working on. The challenges there are different. Obviously, they have to seamlessly integrate with other manned aviation. The third area that we are working on is something we call ETM, which is upper E, which is 60,000 feet and up, traffic management, which is closely linked with the UTM construct of cooperative drone management through intent sharing digital ways of managing or interacting with each other. So in upper E, which is 60,000 feet, you will see balloons, long endurance, high altitude drones, as well as eventually supersonic type of operations. How do you manage them? Because no one provides services in that airspace as well. So that's a third initiative. And then the fourth initiative we have is urban air mobility. How do you actually enable large-scale electric vertical takeoff and landing vehicles in a manner that will scale and will be useful for as a mass transportation, basically, network.
Of the 4 initiatives, are any of them further along than the others?
UTM, which is Unmanned Aircraft System Traffic Management, low-altitude traffic management, sort of automated traffic management system, that's further along. And the high-altitude, or basically what we call US in the NAS, Unmanned Aircraft System in the National Airspace, which is larger drones operating, is also further along. Now, when we say further along, NASA's focus is conducting research, developing requirements, and creating sort of reference implementation details. And then it's up to the industry and FAA to implement them. So our job will be pretty much finished by 2020 in terms of doing the research. We still have the urban air mobility and high altitude Class E type of airspace operations.
How does the work with UTM meld or fold in with the rules that the FAA is developing?
The rules that FAA is working on, the research we do, there's a tight correlation with that. So let me walk through a couple of examples. So FAA implemented something called Low Altitude Authorization and Notification Capability, LAANC. This allows the third-party service suppliers to offer services to the drones. Now, these are not beyond visual line of sight. They are still within visual line of sight using Part 107 rules. That's the first implementation of UTM or US traffic management. So that gives you access to airspace. Now, expanding that, FAA has embraced this notion that we work together on something called USS, which is Unmanned Aircraft System Support Services or service suppliers. These service suppliers basically work together with FAA and each other to provide services to the drone operators. They could be flight planning, tracking and locating them, communications, and so on and so forth. So these kind of service suppliers are also now adopted by the FAA. So that's the second example. Now, moving forward, FAA has released something called NPRM, which is Notice of Proposed Rulemaking. In that, to get to the beyond visual line of sight and flying over people, remote identification of the vehicles is critical. And that identification is critical part of UTM. So you know who is flying in the airspace. You really need to know that there are legitimate operators who are flying and then who the owner is. So that kind of understanding of the identification is important part of the UTM. So that is the first step that's going on. After that, that will enable flying over people, so then you can be assured that the drones that are flying are indeed legitimate drones. And then that allows us also to go beyond visual line of sight, because once you know who they are and once you know where they are, and they are where they said they are going to be, that you can get to beyond visual line of sight. Now, FAA also issued something called ANPRM, which is Advanced Notice of Proposed Rulemaking, which has UTM, Unmanned Aircraft System Traffic Management, called out and said we are looking for comments on UTM and its implementation, different ways of implementing UTM or the sequences. So all those things are in the FAA's rulemaking processes now.
So is it safe to say that NASA conducts the research and recommends the specifications, but it's up to industry to meet and deliver on those specs?
That is a very good characterization, Randy. So we do research, we identify the requirements that will safely and efficiently enable these operations, and then specific implementation are left if it's on the industry side. So third-party services, those are provided by industry, and it's the reference implementation and a connection with the FAA's Flight Information Management System, so they can send in information back and forth to the operators, to the third parties or operators themselves. All that we define based on the research and very tight collaboration, by the way, with industry and FAA, and that gets implemented through their processes.
Is NASA involved in approving or certifying industry standards?
We don't approve the industry standard, but we work together with the industry and provide the data and lessons learned that will help generate the standard. So we are very actively engaged in ASTM standard that's being built for interoperability between the U.S. service suppliers. So how do they interact with each other? So we prescribe the data exchange protocols, the digital means, and such. And how do they connect with the FAA? Now, in Misty's project, she's also working on different things related to the safety and contributions to the information related to the certification. So she might add a few things on that.
Yeah, that would be great. Misty, can you tell us about your project?
Our project, System-Wide Safety, has two parts, and the two parts are kind of based on how we do assurance for safety today. Right now, we do assurance for safety during design, and we have one set of processes and rules for that. And then we sort of throw a whole bunch of ideas and things we need to worry about for safety over the fence to operations. And we have a whole set of different rules and processes that we use for assuring safety during operations. So right now we have about half of our project sort of looking at the operational safety, where we say, as we march forward, as we start to look at all these different kinds of vehicles and all these very new missions, what we're already seeing is that our rules don't apply during operations. They don't make sense. And so to what extent can we, first of all, help figure out what rules do make sense? They're more broadly applicable. And the second part, and a big part of the operational safety, is how do we automate the monitoring for assessment of and mitigation of the safety hazards and risks that we're going to see as we march forward. So that's half of my project. The other half of my project is about the assurance of autonomy. So if you look at what's happening on the design side right now, we have a really hard time implementing highly automated or autonomous systems because those are functions that we've given to the people during operations, and our rules for making sure that things are safe during design sort of preclude you from including those ideas during design time. And so that half of my project is looking at, as you start to include these highly automated or autonomous systems, what design rules actually make sense and still keep people safe. What we know marching forward is that autonomy is a game changer. And really what's happening here, because we're pulling all of this decision-making that was during operations now into decisions we make during design, that means we're going to have to start merging the two different processes that we use right now. And we're going to have to take a more holistic systems approach to the assurance of safety, where we consider operations and design time assurance together.
I read where typical assurance models look at getting the system to do all the right things. But autonomy introduces a new concept that says it's more important to make sure the system doesn't do what it's not supposed to do.
I think that's a great way to think about it. Another way to think about it, if you think about what the real challenge is because we've put all the risky design making and all of our uncertainty into rules around operations, right? We don't certify operators, we license them, we trust them. Well, what we do for software and hardware is, before the idea was to take all the uncertainty and all the decision making out of those parts of the process. So our rules right now, for example, make us walk all the paths. We have to understand all the behaviors of the hardware and the software. And that's not feasible if you're thinking about systems that have to react to weather or have to react to other unknown unknowns.
So how do you approach a challenge like that?
If you look at what we're trying to do right now for the assurance of autonomy, we talk about this as a three-step process. One is to, first of all, understand what the boundaries of whatever sorts of highly automated system or machine learning system or autonomous system are. So to the best we can, characterize safe boundaries. And then the second is to put in place some sort of monitors that can be rigorously assured, that understand what those boundaries are. But you always have to have a failover plan. right? And so when you assure these systems, it'll be in the context of a failover plan. And so the question is, what do you fall back on? Do you fall back on a simpler plan? Is it, maybe you're flying a mission where it doesn't matter what you're doing. If the autonomy suddenly becomes uncertain or operates beyond its bounds, you can always land. Well, that's not always going to be true. So for some systems, you might need to have a human operator always in the loop who can catch and decide. Well, that introduces a whole new can of worms, right? How do you make sure that human operator has all the state information they need and all the awareness they need to actually be able to make decisions? So yeah, NASA doesn't solve easy problems. It's a fun, hard problem.
Is it similar to the way a human being learns? Or does it involve a completely different paradigm? And what I'm getting at is, take, for example, a small child or a toddler trying to learn a set of movements or trying to walk. As we watch, the child might make a decision here, he might make a decision there. We're hoping that it's going to make the right movements and make the right decision. But at the same time, we're also there to catch it in case it falls. Is it something like that, or does it involve a completely different shift in perspective?
So, I think there's a couple of different ideas that are really interesting in what you just said there. One is that there's a lot of different ways that you can imagine either highly automating or making a system autonomous. And so some of those do have this extra learning component in them, where even if you knew everything about them at the time you designed them, they're going to change their behaviors because they do learn over time in the wild. And, the risk there is that can make them more robust. Or, just the same way people are, if you learn the wrong things, it might make them more dangerous. And so there's a big question, particularly around these learning systems, for how are we going to assure those. So that's one way to think about what you just said. Another way to think about what you said that I thought was really interesting is, NASA does have a common, we talk about a crawl, toddle, walk, run approach to as many problems as we can, where we try to sort of identify, okay, if, here's where we want to get to. We'd like to run. We'd like to have the full maximum capability we can imagine. Is there a way to get a progression forward that eventually gets us to that goal? And so we do structure our projects, a lot of our projects, around this crawl, toddle, walk, run approach.
So what are the next steps for your project?
Well, right now we have really active discussion going on with the FAA and other regulators. We're part of quite a few large industry standards groups around the assurance of autonomy. SAE's G34 is one of those that comes to mind. So we've been talking with our industry partners. We've been looking at what are the most likely, what are the current capabilities that we can't assure right now. And when we think about the lowest risk paths forward to get to those capabilities, what are they? So what are the algorithms that we can most easily imagine bounding, for example? And we've done a lot of that work where we've done characterization of different kinds of highly automated systems and autonomy, where which ones do we know the most about? NASA's actually created a couple of very rigorous monitors now. Safeguard is a great example of one of those. It's an algorithm that UAS and the NAS used to demonstrate a very safe geofencing capability. And so Safeguard absolutely guarantees that you won't be able to leave some prescribed area, that you'll stay in a keep-in area and you won't go into any keep-out areas. And the assurance of that work, the assurance of that algorithm was actually done in the safety project. This is another good example of NASA projects working together. So there's that monitor case. And then we've been working with the FAA on frameworks that allow us to make these arguments in a holistic sense, in a system sense. So NASA, for example, created the first safety case that the FAA accepted for a mission called Mesopax. Now, that was a very low-risk mission, so that was part of the reason why the FAA was willing to accept the safety case there. But honestly, the FAA is willing enough to work with us. We have a framework that we've been looking at that we call the overarching properties, that would be an alternative to the certification of these systems, that we think might allow eventually for a framework in which we could make arguments about the safety of highly automated or autonomous systems. And the FAA has created a working group around the NASA overarching properties and has set up large industry groups in that working group to work with us, and hopefully it'll eventually become something that industry can use to enable these capabilities.
Before we close, I want to talk about NASA's Grand Challenge for Urban Air Mobility. PK, can you tell us about it?
Absolutely. Randy, the way you can think about Grand Challenge is analyzing the ecosystem's readiness to support these urban air mobility operations. So when you look at the urban air mobility ecosystem, we want to make sure that the aircraft is ready. We want to make sure that the airspace system is ready so it can scale these operations and provide access to them. And we want to make sure the infrastructure and communities are ready so they will accept them because of noise and other considerations. So the Grand Challenge allows us to take all pieces together. Aircraft, what does it mean by urban capable aircraft? For example, it has capabilities to manage itself either autonomously or with piloted based on the conditions that you will experience in the urban setting. So urban setting has some interesting challenges. We studied those in UTM project where we learned that GPS is not always reliable, communication link is not always reliable in certain corners of urban airspace. So we want to make sure that the aircraft in this case is able to fly those missions that they will typically experience in urban airspace. Now, part of that is also understanding how the battery and electric propulsion system works, how it will continue to support the safe operation, the distributed electric propulsion. So the pieces related to aircraft are all considered in that. Then on the airspace side, as we are expanding the focus from UTM towards UAM, larger urban air mobility, how would these multiple UAS or the support service suppliers will interact with each other when you have more than one electric VTOL aircraft operating in the same airspace? So how do they interact with each other and stay safe and stay away from each other? Sort of share and care type of environment. And the third is the infrastructure and requirements on, for example, vertipad. How long the vertipad should be. If you have multiple pads, how close you can put them without having interference. So Grand Challenge is sort of a progression of series that will study increasingly more complex situations and much more integrated fashion of aircraft, airspace, and infrastructure capabilities so that we can assess what is the readiness of the entire ecosystem so that we can figure out what are the best ways to bring that into the real operations.
Would we expect to see a series of tests in actual urban environments, or will it be more in the controlled airspaces?
Yeah, it will start off with the controlled airspaces, but I think our goal is to think about that as more of a national campaign, and slowly, just like we did on UTM, we went from low-risk areas, remote areas, into the urban areas. And so our dream will be the same, which is to start from the low-risk areas, get a good handle on how these operations would work, and evolve them to increasingly complex areas, including the urban areas. So we have constituted something called UML, which is Urban Air Mobility Maturity Levels. So this is similar to the automation levels that autonomous car industry has. And these UMLs, maturity levels for urban air mobility, basically go from 1 to 6. And 1 is low density, very low complexity. And our research and Grand Challenge series is going to push all the way 1 through 4 maturity level, which is medium complexity, medium density. So all the requirements that are needed on the aircraft side, as well as the airspace system, as well as infrastructure, will be identified and demonstrated through these series of progressively complex scenarios as we go along from UML 1 to UML 4.
Is there anything that we missed that we should talk about?
One thing, Randy, you might want to think about is we are working very collaboratively with FAA, DoD, DHS, but we are also strong believers in collaborative innovation. And for that, we have working groups that include industry as well as other government organizations. So industry members who are interested in providing or testing their subsystems or entire aircraft, they are able to join our work groups. So they can go to nari.arc.nasa.gov/AAM, where you will see, AAM stands for Advanced Air Mobility, where you will see a lot of information about how industry members, academic community test various test sites can be part of our working groups. We truly believe that collaboratively we need to build this ecosystem together. And by joining working groups, they are able to provide inputs, and together, collectively, we can accelerate the transformation towards urban air mobility.
And for my final question, what message would you like to leave regarding NASA's role in the drone industry?
NASA will continue to support safe and efficient operations of all sizes of drones. In Misty's project, the focus is on safety, and as the drones will go more autonomous, figuring out the methods related to assuring that autonomous operation, giving that confidence to regulators as well as general public is critical. And on the airspace side, making sure that these operations will seamlessly coexist with other manned aviation without interfering with each other, and in a safe and efficient manner is something that we genuinely care about, and we will continue to focus on those.
That's it for episode 257 of the Drone Radio Show. I hope you enjoyed hearing from PK and Misty Davies of NASA. I want to thank PK and Misty for taking the time to speak with me. If you want to learn more about NASA's work in the unmanned systems area, or want to connect with PK or Misty, check out the website at nasa.gov/Ames. If you like the Drone Radio Show, please consider supporting the podcast with a small donation. The content is always free, but for as little as $1, you can help defray the cost of production. To donate, go to droneradioshow.com/donate. And thanks for listening. Your support means a lot to me, and I hope you'll listen to more episodes of the Drone Radio Show podcast to hear how others are using drones for business, fun, and research. For the Drone Radio Show, I'm Randy Goers.
This has been the Drone Radio Show podcast. More information on today's show can be found on our website at www.droneradioshow.com. If you're using drone technology for business, fun, or research and would like to share your experience on the show, please visit our website and fill out a guest appearance application. And don't forget to follow us on your favorite social media channels.